be talking about General Leslie Groves. And so an overview for what I'm going to do for this semester. We're going to get 4 talks throughout our semester. And so today I'm going to be talking about his early life and just a little bit of his personal life. And then I plan on focusing on his military career up until the start of the Manhattan Project. My 3rd talk will focus on his role in the Manhattan Project. And that may spill over a little bit into my 4th talk, depending on how long it gets. But I will be mainly focusing on his life post-World War II for my 4th talk. So for today, I'm going to start with his childhood. So Leslie Groves was born August 17, 1896 in Albany, New York, to Leslie Groves Sr. and Gwen Groves. He was the 3rd child of 4. He had 1 older sister, 1 older brother, and 1 younger brother. His dad was an Army chaplain with the 14th Infantry, so he moved around a lot when he was younger. He only grew up on military bases. And then to provide the kids more stability, a little bit later into his childhood, up until he was around 15, he mostly stayed with his mom while his dad moved around. But his dad still had a very big influence on him because he would write letters home to the children very often, reminding them, now this is a quote, to be responsible, brave, honest, and focused on their lessons in school. And so this really shaped his early personality, and I really wanted to touch on this because this will become super important as to why he was chosen to lead the Manhattan Project. So he was shaped from living on multiple military bases, and he also described his family environment as competitive, and so his parents would constantly challenge the kids with stimulating conversation, and they really focused on education. So he was constantly trying the best that they could be and get the most out of life is how he described his parents. And so his parents taught him to value education, hard work, and respect. And respect is super important because of his military career, his family's military background. And he was described by others as a child as ambitious, strong-willed, decisive, and confident, which will all come into play later in his life. So for his teenage years, like I said, around 15, he went to live with his father over the summer in Arizona while he was stationed there. And this is where he found his love for tennis, which he says is a super important part of his life. He played tennis throughout his life. It's where he would make connections, how he would lost speed, and where he had a lot of fun. And then in December, he followed his father to Fort William Henry Garrison, which is near Helena, Montana. And he met Edmund Gregory, who taught courses for the West Point Academy entrance exam for already enlisted persons. And Groves told Gregory of his ambition to attend West Point. So at 15, Groves knew exactly what he wanted to do for the rest of his life. He wanted to go to West Point, graduate, and join the military. So you can kind of see that decisiveness, that ambition coming into play here. It was also in Montana that he met Grace Wilson, who is his future wife. She was the daughter of Richard Wilson, who was the head of the 14th Infantry, so their fathers were really good friends. Their relationship did not start when they met. They were just close friends at first, especially given their close family relations. But they did end up getting married in 1922, which was after he finished a couple tours with the military. She became a kindergarten teacher, and they had 2 children, and they stayed married throughout both their lives. Yeah, she was with him during the Manhattan Project as well. So his road to West Point, which was his ultimate goal up until graduating college, was a little trickier than he imagined. He did everything he could to increase his chances of getting into West Point high school. And so he actually did most of his high school career at Queen Anne High School in Washington. And so it was while he was there during his senior year, he also enrolled as a freshman in the University of Washington to further boost his resume and his application for West Point nicer. So he graduated from high school in 2014 and he took that West Point entrance exam, but he didn't score high enough to get a presidential appointment. And he tried to twice, and it just didn't work out. Both times he was told that the score was too low. So, as a backup, he enrolled in the Massachusetts Institute of Technology as a civil engineer, which I just find so funny that MIT is his backup because now that's just like such a great school. But anyway, and so he started as a civil engineer, which is also super important given the role that he plays in the military. He eventually goes on to be the Corps of Engineers. But while he was at MIT, his education really prepped him for his second try at the West Point entrance exam, and he did get his score high enough, and he got that presidential appointment, and he arrived at West Point in June of 1916. His class then got put on an accelerated path to World War I, and so they graduated in 1918. They were supposed to graduate in 1920. And it was really at West Point that he found his stride as a student. While his parents always put a value on education, he never felt challenged by his classes, especially in high school. He was constantly bored. He didn't really understand the point of just learning this stuff. So it's at West Point that he was like, I'm doing this to, it's a means to an end. I'm going to be in the military, I'm going to be in the army. So like, these are the things that I'll have to know. So he found his stride. He loved the competitive environment, which mirrors that competitive environment he grew up in. So he actually finished fourth in his class. So that started him at the rank of cadet first sergeant, which is the highest rank you can graduate with, or was at this time, highest rank you can graduate with. Which allowed him an early choice of placement. He got his top choice in the Corps of Engineers, as I said, and he'll go on, and this is where my talk will pick up next week. He'll go on to support with the Corps of Engineers in 5 months. That's it for the first one. Any questions?
So I have a question.
Yes.
Has nothing to do with growth, actually.
All right.
I'm tempted to ask this question to everybody. I'm curious what your sources were for learning about it.
So there was an encyclopedia on like encyclopedia.com. There was a really good entry about Encyclopedia Britannica actually. And then there's also this really great source called armyhistory.org. And it has like these long biographies of a lot of people that in the Army. And then also there's this thing called Manhattan Project Voices. And they actually did interviews with like everybody that was associated with the Manhattan Project. And Leslie Groves, I think, ended up doing like 13 1-hour-long interviews. So like there's 13 hours of this interview stuff with the person who was in charge of this project. So there was one specifically focused on his early life. And that's where I got a lot of the stuff about his family. Because he talked about his family, he talked about the competitive environment, his siblings, how his parents shaped him. So that's all. Yeah, that was actually a primary source. Yeah, that was super nice that I found that.
So that is the Atomic Heritage Foundation has that those oral histories. We have 800 oral histories in Oak Ridge. That's online. Center for Oak Ridge Oral History. I'm very familiar with General Grove. Glad you found that useful.
Any other questions?
Did he, maybe you'll come to this later, in some of these interviews, did he speak about his relationship with Oppenheimer?
I haven't looked through like all of the interviews. I just looked through like the first 3 or 4 to find information on his early life. But yeah, I think that I'm pretty sure that in his book he spoke about his relationship to Oppenheimer, so it's surprising if you were asked him about that.
Right. Same from your standpoint. As you go on talking about Oppenheimer, in the end, what was his relationship with Groves? I mean, it was a good relationship, but they're two very different humans. And therefore, it was difficult at times, I assume, right, Ray?
Yes, very much so.
Any other questions?
So, did any of his, how many brothers and sisters did he have?
4.
Did any of them go into the military?
One of his brothers died at the age of 22, so I don't remember if he went into the the military or not. I know obviously his sister did not, and I don't know about the other brother.
And he, of course, built the Pentagon, right?
Yeah, I'm going to talk about that in his career building up to the Manhattan Project.
Okay,
That's reasons why he chose.
good. Anything else? Very good, Courtney. Thank you.
Thank you.
Ray, do you want to start with the story?
I'll tell one about Groves.
Yes, by all means.
One of the young ladies that worked at Y12 happened to be the first female to graduate from UT taking engineering courses. She came here and wanted to be an engineer. They told her she could not complete that course of study and get an engineering degree, but she could get a statistician's degree. So she took those engineering courses if she wanted to and left with a degree as a statistician. She went to work at Y12, and she was the person in charge of all of the data being collected on the Caljatron. And she was the one that pulled it together and provided it to those people that needed to know what was going on. She was working in building 9731. First building completed on the site. It has 2 alpha Caljutrons and 2 beta Caljutrons. And it is a part of the Manhattan Project National Historical Park today. She actually came and helped me to welcome visitors through for a couple of years at least, that we were having visitors come through. And Puckett is her married name, and I gotta get her first name. It'll come to me. But anyway, she was working in 9731, and what she was so proud of is that when we put the displays together in 9731, for people to come by and look, one of the artifacts we used was a calculator. Now, please understand, the calculator back then was about, a foot square by a foot tall and lots of keys on it. And she was so proud. She said, that might not be the exact one I used, but I used one identical to that. And she said, Ray, can you plug it in? And I said, no, I'm afraid to. I don't know what would happen. But she really wanted to see if the thing worked. At any rate, she was there doing her calculations, and someone came in, obviously an Army person, looked over her shoulder, and she ignored the person looking over her shoulder, just kept doing her work. And then a little later, she happened to see a picture of General Groves and recognized that that's who was looking over. So that's one known visit that Groves made. I'm sure he made several. One other visit that was very important to Y12 was when the Alpha Caljutrons first were installed in building Alpha 1, 9204-1. When they installed them and started it up, they shorted out. They just did not work. So Groves came down and looked at what the situation was and told them to take the Caljutrons out, send the magnets back to Alice Chapel, have them rewind them, and have them to use clean oil. And that was a major decision because they were trying to get those Caljutrons installed as quickly as they could. Alice Chambers were building the magnets as fast as they didn't work. So he made them go back and start it all over again. Major setback in the middle of 1943 for the process that Ernest Lawrence had assured him would work. So you got to know Ernest Lawrence was spending time at White Well as well. Just last week, we discovered where his apartment was in Oak Ridge. I have this friend who works in the records department at the K-25 side, and he has access to some of the early records. And it's a hobby of his to find where people lived in Oak Ridge. Significant folks, if he can get that. And I had told him, see if you can find anything that indicates Ernest Lawrence lived here. We know he visited. On one of the visits, he told, he walked in and looked at the Galvatron that was operating there in 9731. And he said, is that the best it can do? And they said, look, it's working pretty good. So he went over and started adjusting. And he adjusted it to increase the output tremendously. So the people watching him said, wow, that is really good. So he was very proud that he'd adjusted the Galvatron up to get much higher productivity. And the person telling the story, which is included in an oral history on that the Smithsonian Institute did, Dr. Chris Hine, telling the story. And he's the one that actually recognized you could separate anything in a Galvatron, not just uranium. And separating copper 63 is the first element isotope separated in a Galvatron other than. But he said after Lawrence left, in about 5 minutes, that thing started sparking and the whole thing blew up. So Lawrence's idea of cranking it up a little higher didn't work very well. That's why they had the young ladies go exactly where to keep that thing, so that it wouldn't get out. So there's your Lawrence and the Grove story.
By the way, so, Ray, you know the lady who wrote that book.
Denise Kiernan.
Right.
Wrote The Girls of Atomic City.
And so we're trying to get her here, by the way.
I had a text from her yesterday, or might have been Sunday, saying that she'd been on vacation and that she would take a look at our schedule requirements this week. So I expect you to hear something.
Great. So you might all get to meet her. So there is a physics meeting, Southeastern Section of the American Physical Society here in November.
Got it. We got November 7th.
Something like that. And the idea is,
Yeah, that's a Wednesday, the 7th.
right, to have Denise Kiernan, who wrote this book, The Ladies,
Girls of Atomic City.
about the ladies who operated the Galvatrons during World War II. And so the physics department is going to invite Denise Kiernan here to give a public lecture on Wednesday night of that week before the physics meeting starts. Ray knows her well, and so it'd be nice to have her come to this class on the Thursday.
Right, see what we can get.
Yeah, I'd like to meet her. That'd be really cool if we could arrange that. Okay, very good, Ray. All right, so let us continue. Okay, remember the history, December of 1938, when the seminal experiment was done in Berlin, showing that when you hit uranium with a slow neutron, it splits into two pieces. A lot started happening at that point. A lot of experiments at different places, a lot of speculation, a lot of questions about what is the nature of that process and could it be harnessed to make a weapon. Because certainly the Germans were working on this same set of questions. Governments were alerted. German physicists alerted their government, and they started a process that I've told you a little bit about. I'll tell you more about. The U.S., Einstein and others, Szilard, alerted the U.S. government, and the Uranium Committee was formed. The first meeting was in October of '39, almost a year after the seminal experiment in Berlin in December of '38. And so it was a set of people including military representatives from the Army and the Navy, to look into what should the U.S. government do? What is the possibility here? It's ironic to me and very relevant that at the first meeting, the physicists present were the three Hungarians, Szilard, Wigner, and Teller, three of these Hungarian Jews that came to Germany to do their PhD work and then had to get out of Germany when Hitler passed the first set of anti-Semitic laws. It was a meeting that was difficult. The military was very skeptical of using this new process to develop a weapon. Generally, it takes a war or two before a new weapon can be developed, tested, and implemented. But they did agree to find some money. There was clearly some money needed to see if you could use carbon to moderate neutrons, because people had learned by this time, in part by mistake, in part by intent, that the best way to make uranium fission is to slow down the neutrons and have thermal neutrons, or very slow neutrons, to make uranium fission. And so the question is, if you were to build a big device, you would need to moderate neutrons. And that was the idea of measuring, having $6,000 perhaps to measure the cross-section, whether graphite would absorb neutrons rather than just slow them down. So that was happening, but it was moving slowly in the U.S. No money was committed. This is October of '39. So the process was proceeding very slowly in the U.S. In England, there was a parallel process, once again driven by immigrants, by Jewish immigrants. Otto Frisch was a nephew of Lise Meitner. He had left Austria before Hitler took Austria, gone to England. First he went to Copenhagen, worked at Niels Bohr's Institute at the University of Copenhagen, but then he feared Denmark being next to be invaded after Austria, after Czechoslovakia, after Poland. So then he went to the UK, to England, and he got a job being a lecturer at the University of Birmingham. Also at Birmingham was Rudolf Peierls, another German Jew who had left Germany and went to England. So Bohr, the great Niels Bohr, felt that it was uranium-235. That's only 1 out of 140 atoms in natural uranium is mass 235. Bohr felt that was the isotope that was fissioning. And Bohr therefore felt that it'd be impossible to separate uranium-235. And also, Frisch thought that this process, if you could multiply neutrons, if you have a chain reaction, that would be much too slow. It would never be a bomb. Peierls was working at Manchester, so they got together in Manchester, and Frisch had no money. He actually lived with the family of Rudolf Peierls, but they began working together, and it's a very important partnership because Peierls was the first to calculate the critical mass of uranium. If uranium did emit neutrons, and there was some hint that it did emit 1 or 2 neutrons, then you might be able to chain reaction. But how much mass of uranium would you need to make a explosive device? And he published this. The answer was a lot. If you had natural uranium, and the Bohr's right, is only 0.07% of natural uranium was a fissionable isotope, then you would need tons of natural uranium to make a critical mass to make a weapon, and that was not good. But still, it was a question of what was the fission process. You see, and this is a little confusing, I agree. This is what the physicists were debating, that you had uranium-235, 0.07% natural uranium. But most of the natural uranium is uranium-238. You had fast neutrons and slow neutrons, and this is Bohr's blackboard sketch for the physics of the process. Uranium-238 does have, the feeling was, a cross-section, a probability of capturing a neutron and thus fissioning. But it was known that there was a resonance here, that if the neutron lost its energy, scattered around, bounced off of things, and hit this energy of 25 electron volts, less than 1 MeV, less than 1 million electron volts, the neutron would get absorbed. And you would never be able to make use of this likely high probability of fission at low energy. So there was this slow neutron fission of uranium-238. Bohr thought that that was not possible. Fast neutron fission of uranium-238. Frisch thought that that was not possible because the neutron would bounce around, lose its energy, and get sucked up, not causing fission, but being captured by uranium-238. But then also would uranium-235, people were getting pretty sure that at low neutron energies, if you could moderate it, that would have a big probability of causing fission. People were ignoring this, however. And so that was the question, to do a calculation of what is the probability? How much mass do you need? And Frisch and Peierls worked together, and they calculated that the probability of capturing a neutron is just proportional to the size of the uranium nucleus. So if this is uranium-235, if a neutron comes zipping by there, and if it misses, then you do not have absorption and fission. But if it hits anywhere in the uranium-235 nucleus, then it would get absorbed. And fission would occur. That's the geometric cross-section. That this was so likely that as a first guess, that the probability of a neutron causing uranium-235 to fission, moving slowly, is just the size of the nucleus. And that size is about 10 to the minus 23rd, minus 23 square centimeters. Well, that may not be exactly correct, but it's a good first guess that if you have a collision, that slow neutron is going to get sucked up by uranium-235 and fission will occur. And so that's what Peierls then and Frisch calculated. And they were shocked, if you do that calculation, how much mass do you need? Not tons, but pounds. And so that was a very surprising result, that you needed only pounds. Let me move this window around here, sorry. grid that new bill. High video panel, that's what I want to do. Nope, it's not it. Yeah. So with that assumption that a neutron hitting the nucleus would cause fission, then you got the shocking result that you only need a few pounds to make a bomb, perhaps, of uranium-235. And then it calculated the time. You know, the question is, how fast would this occur? If you get neutrons emitted, uranium then fissions, goes into two pieces, fission fragments. It's about half the size of uranium. And then if you have one or two neutrons also emitted, then those neutrons can cause a chain reaction, cause other uranium nuclei to split into two. And as answer, you got a shocking result also, that'd be fast. If it were a slow process taking half a second or milliseconds, then the explosion that would be so slow that you'd have the chain reaction be too slow, and you'd have a explosion driving apart the hunk of uranium, 2 pounds of uranium, before you could have a critical mass and a big explosion. And so that was a shocking result, that you don't need that much material. If it's uranium-235, a few pounds, and it's fast. And for the first time, it said that you might be able to have a bomb that would be possible. And so, especially if you use fast neutrons, that fast, if you're using slow neutrons to cause uranium-235 fission, that's what I've been focused upon. But if you use fast neutrons without a moderator, then that produces the speed. And the explosion could happen very quickly. You could have a bomb. Now, this was, no one else had thought about this. So that if you could make a bomb, you could use fast neutron fission of uranium-235. Slow neutron fission of uranium-235 would be too slow to have a chain reaction to go within microseconds. But fast neutron fission would work. And the advantage is you don't need a moderator. You can't build a bomb if you have to have whole light graphite to slow down the neutrons. Well, that was a shocking result. Other Frisch and Rudolf Peierls been published. Fermi and Szilard working together in New York and Columbia, they were still assuming that you would use natural uranium to make a device. And Frisch and Peierls were showing that that just wouldn't work. Well, so that was their conclusion, February of 1940. Barely, just a little more than a year after fission was first realized, discovered. But then, how do you separate uranium? That's the big deal. Uranium-235 is only 0.07% of natural uranium. So Peierls and Frisch show that you only need a few pounds of that stuff. That happens rapidly. You don't need a moderator. But how on earth would you get enriched uranium-235? Otto Frisch read papers on gaseous diffusion by a German chemist named Klaus Clusius. And that the idea is that if you have a glass tube, if you heat up uranium hexafluoride, uranium in a gaseous form, that as a function of temperature, they would all have the same temperature, but uranium-235 in a chemical compound is lighter a little bit than uranium-238 in a chemical compound. You heat them all up in a glass tube, the frequency with which they strike the walls is different. And the lighter molecules, that is containing the lighter isotope, will strike the most walls more frequently. You can put some holes in this glass tube, and you might be able to get more flow out of the glass tube through those little holes with uranium-235 in some chemical compound. That's what thermal gaseous diffusion is. And that sounded unlikely, but then when Frisch dug into the work of Clusius, he figured out that, well, yeah, you may need 100,000 of those glass separation tools with little holes, but you know, that's maybe not so bad. Maybe that is achievable to get a pound of uranium in only a few weeks. So if you had 100,000 of those glass tubes, you would be able to separate uranium-235 in some chemical compound from uranium-238. So that was also a striking result in 1940. So all of a sudden, and so they wrote a report to the British government, to a committee. Yeah.
It's not random, but like, did Hitler not have an issue with his side, like scientists from Germany posting their results that concerned with nuclear bombs? Like, was he gonna keep that really private?
Yeah. Yeah. Well, that's right. But by this time still, no one really knew what was the possibility. So all of this stuff is still being published by 1940. And then not long after this, they realized that this is moving rapidly. So sometime later in 1940, people stopped publishing in the open literature. Hitler was more focused on taking over the world. And so his scientists were still publishing stuff. But that stopped pretty soon thereafter. So Frisch and Peierls wrote this report about what they call a possible super bomb. They sent it to, this was not published in the open literature, but it was a report to the British government, to a committee of the British government. And they said that, of course, if you could build this, there's no shielding that would be able to guard against this. It'd be so powerful that there would be no way to shield against it. By the way, if you could build a bomb, you'd have a lot of radioactive fallout. You know, these fission fragments and uranium splits. These two pieces are radioactive, some with short half-life, some long half-lives. So they realized right away then that you would have a whole lot of radioactivity spread around the countryside of the city if you could build a bomb like this. They point out that Germany is probably working on this also. And if Germany's working on it, then England has to work on it. Because the only way to protect yourself, you can't protect yourself by shielding if the Germans develop a super bomb. The only way to protect yourself is by having one of your own. And so, you know, this, in some ways, this report was the beginning of the new arms race, that if your opponent has such a super bomb, you better have one yourself, because you're not going to protect yourself against their weapon. So this was said, by the way, this has all been torn down now, but gaseous diffusion, that I said was Frisch came across and thought might work, did become, after World War II, the uranium enrichment process of choice. And that's K25. We're going to show you Y12 and X10. K25 has all been torn down, the site's there, but these buildings have been decontaminated and deconstructed. That's where then from end of the 40s up through the 80s. That's how the country enriched uranium for our nuclear power industry.
Lee,
Yeah,
how well known is the physics of nucleus storage? You don't always get the same products.
mhm.
Do physicists know why you get the products you get, how they happen in the nucleus?
Pretty much. It is a statistical process. And what Mark is referring to, you know, there's these fission fragments versus mass. There's two humps. And so you have uranium-235 that fissions. And so, and this is element 92. So the two products have the sum, have the same number of neutrons and protons. And so, but you have a distribution. There's something around barium and something heavier. But it's not just one. If you've got this one happening, then this partner would be a little bit heavier. Or if this one happens, then it's that one. So there's a statistical variation. You can calculate that. It's more empirical rather than first principles. Okay. And it depends also, as you know, on what it is fissioning. Uranium-235, plutonium-239, californium-251, 252. They all have different distributions. So that's pretty well understood. Things are happening fast in Germany. Things are happening slow in the US. I said when that first uranium committee met, it was contentious with the military there and the scientists. They didn't agree, nothing much happened. In England, you know, Pearls and Frisch sent this report about the super bomb of the British government. At the same time, things were happening in Germany. The first meeting there was in September of '39, and German physicists alerted the War Department about this possibility. December 39, that's only a year after a seminal experiment there in the same city, Berlin. He said that you should be able to, they met in September, then they all went off to study different things. Heisenberg reported that you should be able to build a reactor using natural uranium. But you needed a moderator. You needed carbon, pure graphite, or you needed heavy water. Well, that's what Fermi and Szilard were working on at Columbia University. They were working on carbon. It would be a good moderator to slow down the neutrons. These neutrons come out with energy about 1 million times too high to cause other uranium nuclei to fission in a chain reaction, so you got to slow them down. That's the purpose of carbon or heavy water, not H2O, but D2O, curium oxide. If you enrich uranium in 235, you agree with Bohr, which is mentioned before the war, that it was uranium-235 that fission, you have a smaller reactor. To build a bomb, he said that you would need to enrich uranium-235 to make it small enough. In that sense, he agreed with Pearls and with Szilard, and maybe he even came to that conclusion earlier than they did. They got a ton of uranium oxide ore from Eastern Germany. They also were working on gaseous diffusion. They knew about the work of the German chemist Clausius. So Paul Hartech was working on that also, just like Otto Frisch was thinking about that in England. Paul Hartech concluded that heavy water would be a better moderator. The problem was that Germany had no heavy water plant, and to extract heavy water from natural water, you need a lot of energy. It would take 100,000 tons of coal in that process to extract 1 ton of heavy water. There's no way Germany could pull that off while they're invading countries and feeding a war machine. So they looked to Norway. That's one reason Germany took Norway, because there was a heavy water plant in Oslo. It's called the Mork hydroelectric power plant. It's 90 miles west of Oslo. That's how the building looks now. This is how it looked in World War II. It was built in 1911. The main purpose of that hydroelectric plant near Oslo, there's a lot of mountains and rivers you could dam up in Norway, and so they built this in 1911, Norsk Hydro, as a way to make heavy water that would be used to fix hydrogen for fertilizer. Part of the chemical process to make fertilizer, you needed heavy water. It was the first plant well, maybe it was a byproduct, first plant to produce heavy water as a byproduct of making hydrogen used for the Haber process to make fertilizer, to make synthetic ammonia, which we use as artificial fertilizer. So it's a byproduct of the Haber process. And the Germans knew about that. The Germans took Norway. Before they took Norway, they offered to buy the stockpile of heavy water. There's 50 gallons on hand. It was worth $120,000. And they may place an order of another 30 gallons per month. This is before Hitler took Norway. They wouldn't tell Norwegians why they wanted to buy the existing heavy water and why they wanted this plant to make more heavy water. But they told the French colleagues about it. Joliot was the nuclear physicist in Paris who's working on trying to understand fission also. Joliot told the French government about the Germans' interest in buying all the heavy water that this plant could produce. And they alerted the Norwegian king that the Germans were up to no good. This must be somehow related to fission and building, see if you could build a bomb or whatever. And so they decided they would give the deuterium, this supply of heavy water, to the French. Getting out of Norway wasn't easy because the Germans were watching Norway, suspicious of plans to derail their scheme. And so they loaded up 2 airplanes with the 26 cans of heavy water. They had a decoy that went first that didn't have anything. The Germans stopped that plane, searched, found nothing. But the other plane had this real plane with 26 cans of deuterated water. And that worked. They got it to France and got it out of the grasp of the Germans. So at that moment, they were safe on keeping heavy water out of the hands of German atomic bomb project. By the way, other countries were reading the literature and working on fission also at this time. There were experiments published in June of 1940 at Kurchatov Institute in Russia. There were in Japan. They were following the literature. There had been Russian, of course, scientists working with Germans and Danes and whatever before Hitler started taking countries, also Japanese. And so the Russian government and the Japanese government all had their scientists working on assessing what are the possibilities for a weapon. April 1940, Germans took Denmark. Then they took Norway. There was no resistance in Denmark. The king of Denmark realized that this was hopeless. They didn't have a real defense. They were hoping to protect the 5,000 Jews in Denmark. This is Scavenius. Erik Scavenius was the Danish prime minister in 42 to 43 with the German leader of, or ruler of Denmark, the guy official, the Nazi official that was overseeing Denmark while they occupied Denmark. This is a neat photo of me when I finished my PhD in 1968. I got a chance to go for a year to the Niels Bohr Institute in Copenhagen. Spent a year there. At that time, the best place to be in the world if you were a young nuclear physicist. And we had, my wife and I had a child who's now 51. She was a year old. We rented an apartment in Copenhagen, and it was the apartment of his wife. He had died by 1968 we arrived, but Fru Scavenius lived there. And I never met her. We just rented her apartment through the Niels Bohr Institute. But by reading up, I realized that she was the widow of the prime minister of Denmark in that period. And of course, this is right down the street. This is a Freemasons lodge on Blågårdsvej, just down the street from Niels Bohr Institute. I'd walk past this every day on my way to the Institute. There's a Danish flag, of course, the Nazi flag, so that was their headquarters when the Nazis occupied Denmark. But the Danes did not put up a resistance. There's a wonderful story in a museum. And so the Danes did not put up resistance, but the Danish underground worked very hard to primarily protect the 5,000 Jews in Denmark, and that was kind of the deal. The Danes did not resist the Nazis coming in, but in return, the Nazis would let the Jews alone in Denmark instead of sending them to the camps when they got killed. That was a tenuous truce, unspoken. Then, at some point, the Nazis decided that it was time to take, and the Germans were willing to do that because they needed farm products from Denmark. Because it was hard to grow stuff in Germany with all the war going on. And so at some point then, they decided that they needed to take the Jews. But there was a member of the Danish underground working in the Gestapo's office in this building. And so she heard about this, passed the word to the Danish underground that tomorrow night they're going to come and get the 5,000 Jews in Denmark. And it worked very well. The underground got the 5,000 Jews out of their homes, hid them in farmhouses and such. So when the Gestapo came and knocked on the doors, they were all gone where they were living. And then over the following weeks, they ferried the 5,000 Jews over the Øresund, over the sea to Sweden, which was neutral. And so there were essentially no Danish Jews that were lost during World War II through this heroic work of the underground. In England, that report on the super bomb done by Otto Frisch and Rudolf Peierls was sent to the Tsar committee was called. He was the guy that formed this, the government leader. Thomson, the son of J.J. Thomson, who discovered the electron, was the chair of the committee. He worked at Imperial College in London. They met for the first time in April of 1940 to hear how, among other things, to discuss that report, but to also hear about a visitor from Paris telling them of this story about Germans wanting to buy heavy water from Oslo. So they knew the Germans were working on something related to fishing. They discussed at the April 24th meeting some more calculations Frisch did showing that the if you get enriched uranium-235, you could probably build a bomb. The question was, what is the fast neutron cross-section? Probability of fission. Uranium-235 versus energy. This is for slow neutrons if you moderate them. That's the question. What's the cross section for fast neutrons? That was unknown. And so that was the idea. James Chadwick, who discovered the neutron, was commissioned to use the newly built cyclotron at Liverpool University to do that measurement to assess what is the fast neutron cross section. If you could separate uranium, would it really work? And so they were advancing rapidly. See, they didn't have the military involved in this committee. It was in the US slowing things down, dragging their feet, saying, this is a waste of money. We know how to fight wars. But the military in England was not involved. And so they were proceeding through a sequence of events in England to see if you could build a bomb from uranium fission. Nothing was happening in the US. Finally, after a year, $6,000 was provided by the military through the work of the Uranium Committee so that Szilard and Fermi at Columbia could test graphite, carbon, to see if it would work as a moderator. Would not work as a moderator if it captured neutrons too much, sucked up neutrons, then that's not going to work as a moderator. Szilard went out to Long Island to see, went to Princeton to see Einstein again, to send another letter to President Roosevelt that to update him the fact that the Kaiser Wilhelm Institute in Berlin, there was rumors that there was uranium research going on, but it was a slow-moving process in the US. One thing that was happening is the idea, another professor at Columbia, John Dunning, was working on studying uranium hexafluoride, natural uranium, this chemical compound. And sending it, that's off, it's a gas at 140 degrees. He sent it to his colleague at University of Minnesota, who was experimenting with mass separation. And, you know, if you put uranium hexafluoride here in the ion source, as Ray described before, the path, in ionizing, the path through the magnet would depend upon the mass, and thus you could separate, do a little bit of separation of uranium-235 hexafluoride from uranium-238 hexafluoride. And they were able not to do a full enrichment, but he was able to do a slight enrichment, sent that slightly enriched sample back to Columbia, and they did more measurements, Fermi and Szilard then, to show that it was indeed uranium-235 that was a fission isotope. And so this was another way to verify that Bohr was right, and that it's uranium-235 that fissions. Finally, then, $6,000 was appropriated by the military to allow Fermi and Szilard to do a measurement to see whether graphite would work as a moderator. Then they decided they would just wait on that. So this is already April of 1940. Things are moving very slowly in the US. You know, at the same time, a lot was going on in Europe in the spring of 1940. After the Germans marched into Copenhagen and took Denmark in a peaceful way, they moved to take Norway. And there was resistance in Norway. But of course, there was not, the British government said that they would support Norway. Neville Chamberlain was still the Prime Minister of England, and he was the one that tried to negotiate with Hitler, thinking that what Hitler only wants is a German-speaking part of Czechoslovakia satisfied. Of course, he was not. So Chamberlain was criticized widely for being an appeaser. And then also, the British government, British military did very little to slow the German occupation of Norway. It was all that heavy water. So Chamberlain was getting less support by his own Conservative Party. And then in May 10th of 1940, Hitler invaded Holland, Belgium, and the Netherlands. He had gone east, now he's going west. Of course, he had a set sight on England, the sight set on England. So on that day, then Chamberlain also lost confidence in the House of Commons. And so he was booted out as Prime Minister, and that's when Winston Churchill took over as Prime Minister. Things were really getting bad at this point. The Germans were attacking France. Planes came in to try to bomb Dijon. They got confused, and they dropped their bombs on Fribourg in southern Germany by mistake. Bombed their own city because the weather was bad. The Germans blamed the British. Standard government procedure, they blamed the British for bombing Dijon, or bombing Fribourg. And so then Germans vowed retaliation because the British, they say, bombed Fribourg. It's their own planes that did it. So things really heated up. There's a movie about this. Did you see that movie? What's that called? There was a recent movie about this in the last 2 years about the Dutch resistance. Hitler got into Holland, but there were resistors in Rotterdam in Holland, and the Germans, they were holding out, and so the Germans were negotiating to spare their lives and let them surrender, but someone missed a chain of command, missed an order, and so the German planes attacked and wiped out those resistors in Rotterdam. Well, that then prompted the British to do airstrikes in the Ruhr Valley, retaliation for this cruel act of just killing these resistors. And then in June, things were heating up rapidly. Italy invaded France from the south. Germany was invading France from the east, and then Italy declared war on France and the UK. So France surrendered in June, and then Germans and Italians moved in and divided up France into different zones. And of course, they were planning on attacking England next. The idea was that the Germans would invade England, but they would soften up the UK for invasion by first doing air attacks on the UK. And that was the Battle of Britain. So you see, spring and summer 1940 became very difficult times. Battle of Britain began in mid-August. They intended to invade. The Germans intended to invade in September. And there was a month of air battles. Initially, it was not focused on cities. The Germans were attacking British military installations and airports. British and Germans were attacking each other's military bases and airfields and manufacturing facilities, but not civilian populations. And then August 24th, a mistake was made again where German planes were trying to drop bombs on oil storage tanks not far from London, they overflew their target and dropped the bombs on London for the first time. Then England responded by air raids on Berlin after that mistake. Hitler got very mad about that. And so then the Blitz began, the Battle of Britain began, where they delayed their air attacks on Britain initially in the day, but that didn't go so well. The Germans were losing too many planes, so they started night bombing of cities in England, especially London. So this went on for some months, from September to May. Every night, there were bombs dropped on big cities in England. That's the Blitz. And so 20,000 people died in London and 23,000 elsewhere as the Germans dropped 200 tons of bombs on English cities every night for 6 months. I've got this poster hanging in my garage, this famous poster. Well, here's St. Paul's Cathedral, with people watching for the German planes coming in. Here's a wonderful picture of St. Paul's Cathedral, where everything around it was destroyed by German planes, but St. Paul's Cathedral was never hit. So that's a great photo of destruction around St. Paul's Cathedral. But, you know, the Brits did not crack. Churchill was in charge, which is, you know, the Germans were coming, but they didn't lose their resolve, and they resisted the 6-month Blitz by German aircraft. So that was the politics going on as all these other scientific endeavors were going on to try to mount experiments and see if you could really build a atomic bomb. Okay, so maybe we should stop there.